Okay, guys, we're gonna go today into our probably the most important introductory type of lesson of our year. It's called the mole. Accounting concept, I think, is the title in the book. So I'm gonna use the note that I've made for you guys as well. That I'm gonna have them follow along with, and we're gonna tie it in a little bit to the mini investigation that I left for you earlier in the week. So if we have a reaction where it's H2 plus Cl2 gives us two HCl's, we know that that means one molecule of hydrogen combines with one molecule of chlorine to give us two molecules of hydrogen chloride. We've looked at that a bunch of times. So what we want to look at is now how many actual molecules are in certain amounts, but trying to count individual molecules. So we saw in what you looked at in that mini investigation, where you're estimating number with grains of rice and with beans, how many were in a particular sample. And that probably worked okay as you saw, but if we start talking about grains of rice in a kilogram bag, now your estimate could be off by hundreds, which is significant. So because of that, one of the things that I wrote here, our little notes as kind of a summary, is that mass, it only gives us an estimate of the number of entities in any collection. So, it's only an estimate. Mass is only giving us what we did in that mini, or what you did in that mini investigation. Well, it really gives us an estimate of number of grains of rice in, say, this whatever particular sample it is. So if we took 500 grams of any one substance and we wanted to count the individual molecules in 500 grams of any substance, it would take you basically an entire lifetime to count that. That's how many are actually in there. So we need a better way to count. And if you look at in your note where they have the tennis balls and golf ball example, you can go through that one. Again, it just basically is telling us that mass is just an estimate. So what we need is another way of counting. And what we came up with is what we call the mole. Okay, and the mole is an SI, that's Standard International. It's the unit for the amount of a substance. We use the mole. Okay, and 1 mole equals 6.02 times 10 to the 23 entities. So that can be tennis balls or golf balls or grains of rice or beans or elephants or ions of sodium or atoms of nitrogen or molecules of carbon dioxide. Can be literally any entity anywhere. But think of this number, 6.02 times 10 to 23. 23, you got to move this decimal place. So you're talking about 1, 2, that would be 602, and then 21 zeros. Like a billion only has 9 zeros. So we're talking 21 zeros. We're talking a massive, massive, massive amount of entities. So the other diagram in the note that they look at is if you take, it doesn't matter. So it doesn't matter if you take a mole of elephants. It doesn't matter if you take a mole of carbon. It doesn't matter if you take a mole of water. If you take 1 mole of each one, there's the exact same number of atoms or molecules in each of those. So there's in a mole of elephants, there's 6.02 times 10 to the 23rd elephants. In a mole of water molecules, there's 6.02 times 10 to the 23rd water molecules. In a mole of sodium atoms, there's 6.02 times 10 to the 23rd sodium atoms. Now, if you take, for example, I think in the diagram that I've given you, the one in the tube, volumetric cylinders, it's carbon and sulfur atoms. And you'll notice that there's a mole of each, mole of carbon atoms in one cylinder, a mole of sulfur atoms in the other one. And you'll notice that the sulfur takes up more space. It's more volume. And that's because, one, sulfur atoms are larger, as we learned way back in chapter 2, I think, because of their atomic radius, they're larger, and they also have more protons and more neutrons, and therefore they're also heavier. So that's why they're going to take up more space. But even though there's in that diagram, there's this much full of carbon atoms and this much full of sulfur atoms in the cylinder, there's the same number of atoms, 6.02 times 10 to the 23rd, because it's 1 mole of each one. Okay, so that's really important. It doesn't matter if you took, the same logic applies if you took 1 mole of golf balls and 1 mole of tennis balls, the tennis balls would take up more volume because they're bigger. So hopefully that makes sense. Now, we're talking about this in terms of these real things like tennis balls and golf balls. To give you an idea, if you took a pea, I think we've all seen what peas are. To me, they're the most disgusting food in the world because they like ooze in your mouth when you bite them. So gross. Totally beside the point. But anyway, 1 mole of peas. Okay, a mole of peas, 6.02 times 10 to the 23rd peas. If you had 250 of the planet Earth, you could cover every single one of those 250 Earths to a depth of 1 meter with peas. A meter is like this big. So you could have this much, this deep of peas across, over the entire surface of the planet Earth, 250 times. That's a buttload of peas, right? That's how many molecules are in a mole, or atoms or whatever are in a mole, entities in a mole. So a mole is massive, how many there are. That's why it would take a lifetime to count them. Okay, so some of the stuff that's on here today is counting with scientific notation. So when you multiply two numbers together, and I'll just give you the example that they have. If you have 2 times 10 to the 5th times 7 times 10 to the -8. Okay, remember some of our math rules from back in grade 9. We multiply these two, that's 14 times 10 to the, we're adding exponents, so 5 plus -8, which is 14 times 10 to the 5 plus -8 is 5 minus 8 is -3. Okay, now this, however, not in scientific notation. Remember, scientific notation has to be between 1 and 9.9. So we need to change that to 1.4 times. Now, the exponent's going to change because the decimal changed. Okay, so here's the thing. This is the general rule that I use to remember. If the numerical portion, 14, gets smaller, which it did, 1.4 is smaller than 14. If the numerical portion gets smaller, the exponent increases by 1. Now be careful here, -3 goes to -2 because -2 is greater than -1. Okay? So my general rule is if the numerical portion gets smaller, the exponent gets larger, and vice versa. If the numerical, if we're dealing with a decimal number, 0.41, and we make it 1.41, then this number got larger, decimal, or the exponent gets smaller. Okay, so you're going to have a lot of this. It's always got to be in scientific notation. We're going to see a lot of it because we're dealing with the mole. Okay, so that's pretty simple. I'm going to give you that one. And then next week, I think I'm going to have a couple of lessons, but some practice questions just working with the mole for now. And then we'll get into some other stuff very shortly. Okay, good luck.